Okay, let me continue with this series of videos, and the result at the end of the video, which will be also the end of the first part of this series, and I will give you this assignment, this exercise to complete. This is what you will have. So you will have points that are going in a certain direction, and they are leaving behind a kernel noise field. So super simple and interesting to look at, especially when you will be able to give it some color. But yeah, let's try to understand how to achieve this type of simulations. And this should be your basic setup, and this should be what you have in your file. I added some nodes, and by the way, if you click and you press L, you can like organize them. And already, as I told you, if you press Shift S, you can change the way that the cables look, and I prefer this smooth curvy connection. I've added a node called resample, and I'm going to explain you what this node is. And let's see, this should be the same code that you have in your file, more or less. In this case, I think I removed the frame, the simulation running only if the frame is less than a certain number. So in this case, the simulation is running forever. And yeah, this should be the same code that you have in your file. And probably you don't have this stuff. This is just kernel noise, but with some little animation, and I will use in this lesson we will basically write this code, and then we will write the advection, super simple basic advection using this simple formula. And so one thing that I want to show you is that when you write something in your Wrangle, you can save it as a recipe. So I'll show you. If you click here, this little button here, you'll see some preset. And recently I'm trying to store all of my code inside of a preset, but still I don't have many. I have this one, and this one. Let's click on kernel noise, and you will see you have the code for the kernel noise. And to save it, I will show you. First of all, let's write the code. So let's delete. Let's first of all analyze. We have variables called frequency, offset, and pause, which will be the position where we will be using to write the noise on top of it. And then there is this variable defined as a vector 4. A vector 4 is a vector with 4 components, and 4 components, and x component, y component is 0 because we want to denoise, on X and Z plane. Then there's this Z component, and then there is the fourth component, which is the time. And you can animate by using at frame attribute frame with the capital F multiplied by some speed value. And remember that to create a parameter, you need to click here, and you will create all the parameters that we wrote inside of our code. So the frequency, the offset, and the speed. Let's write our noise code. So let me delete this wrangle. Let me create another one. And to make a noise, we need frequency, vector frequency. So let's define a frec variable. GHF, let's call freq or frequency. Then let's declare an offset. An offset is like if you want to offset the position where to calculate the noise in order to have different results, different patterns, because the noise is to calculate a noise field, we need a position in this case, because the noise field is using a position. If you write the function, for example, just to let you know, and you can see that cur noise computes divergence free noise based on parallel noise, and to use it you need a vector, and the position is a vector, so you can use the position to write the noise. And of course we want to have this noise to have this noise to offset our position vector. So it makes sense to calculate the noise on top of the position vector. And let's create the vector 4. Vector 4, let's call it vec4. Before creating the vector 4, so vector 4 is a variable. We can define vector 4 variable, but before creating it we need the position vector where to calculate the noise. And I can use @p, but for good measure and for clarity, to keep things clear, I will use clean. To keep things clean, I will use vector. I will define a variable called pos, and this variable called pos needs of course the position vector, wants the current point position, and let me check. And as you can see, we are multiplying the frequency and adding the offset directly on this pos vector. But actually you could do this also here, but let's do things the same way that I did here. So this position can be multiplied by the frequency, and you can add on top of this an offset. You should learn this type of of stuff when dealing with kerr noise, because a vector can be multiplied by a value, and this multiplication will affect the frequency, how frequent the divergence and the curling of the noise will be. So if the frequency has a high value, so the noise will be really noisy, while if the frequency has a low value, the noise will be smoother. And if you, on top of this multiplication that will affect the frequency of the noise and the look in terms of noisy patterns, you can add on top of this the offset that will again offset, and it will give you it will translate, let's say it will translate the noise. Therefore an offset should be better to have vectors instead of vectors instead of a float. That's why here I did it wrong, because this is a channel float, so it's better to have a channel vector, because an offset can be in the x direction, in the y direction, and in the z direction. Of course, the y direction, we are not interested in the y direction, and we will not consider the y direction, but it's good to have it, and it's good to have all direction. And also the frequency, you can increase the frequency in the x direction, or in the y, or in the z direction. So now that we have this, we can create a vector 4 called vec4, and this vector 4 is again a vector with x, y, z component, but also the fourth component. So let's first of all define the components of this vector. And you remember that we can, if we have a vector free, just call it vector, call it pos, we should define like set pos x, pos y, pos z, and we can define its variable here with the set function, or you can write its component like that. Okay, in this case we need to set 4 components. So set, of course, pos.x, pos.y, which is 0, pos.z, and the fourth component, which is time, or you can use frame, and those have time and frame attributes are different. I think I'm not very good at this stuff, but I think the frame is actually the frame that you are at, so it's taking in consideration the actual frame and the actual timeline, while the attribute time, it should take in consideration also the substeps, and it's complicated. I'm not very interested in this stuff. I use them both and they give me different results. So I just check which is better. But if you have a better explanation, you can write in the comments and please let me know, teach me this concept, because I needed to understand it, because it's not good to not knowing really well what the frame and what the time are. But again, I think the frame is referring to the actual frame you are at, while time takes in consideration, first of all, is measured in seconds, and it takes in consideration also the substeps of the solver. By the way, you can multiply this frame by a channel float. This time it's a channel float because we want the speed. And again, remember, you can call this whatever you want. Fast, you can call control time, you can call whatever you want, but speed, I think it's intuitive. And now you see this is same stuff, and now you want to create the noise with the current noise function. So vector noise is equal to current noise, and use this vec4 to perform and write the current noise. So let's write the current noise considering this vector, which is a vector 4 that takes in consideration also the time, the frame, and so it's animated. And now, if you want, you can write a velocity. I mean, if you want to call it velocity, you can write this noise as an attribute, and you can call it velocity just to visualize it better, but you can call it whatever you want. Velocity is just a vector, and you can call it also, for example, noise, which is exactly the same, but in this case we're gonna call it velocity. V at V is equal to noise, and this is the wrangle. And you can multiply by the time increment, which again is like, I consider this as a delta t. If you consider like physics and formulas, you see that the for example, you can find delta x, delta t, delta v, and the delta is like the current velocity minus the previous velocity. And time inc, delta t, so it's the current time step we are at minus the last time step. So it's the time increment, and I use it to make things more physically accurate in some cases. But we will talk about those stuff when we will be dealing with integration methods and some formulas, but it will be in the future, not now. Let's focus on basic stuff. And so this is the code. You can save this code if you go and press the right mouse button and click on recipes, and you say save parameter preset, and you can leave it this as it is, like default, but change the name, and you can create current noise, for example, and save. and you should see here in this menu. Now that we have this, you can multiply by the time increment, and then you can advect the position. So position vector, so our current position, so the points should be moved, so plus equal the velocity, and that's it. If you notice here, we set a point group for those points, putting those points into the sim group. So this is just to say, let's simulate only the points that are not in the process group, because as you can see, we are removing ptnum from the process group. So it's the same as saying work on every point but the process group points. And you can now write sim, so in order to work on sim, just on sim only, but you can also do that process, so work on everything but process. This means everything but, okay, the exclamation mark. And use this to make parameters and write values like this, for example. And if you want, you can, with the middle mouse button here, move this slider like that. You can do for every single parameter, for X, for Y, for Z. And you can see that if I middle mouse click, you can also go top and bottom. And this is just, for example, I will increase by 100. If you want to increase by 100, if you want to increase by 10, or decrease by 10, if you want to move by 1, and so on. And yeah, so now there is this resample node. If I remove this resample node, now you have everything and you are advecting your stuff. So I can delete this one. You are advecting your stuff, and if I press play, you see it sucks, because the points are there are few points, and they are going to be too much distant between each other and certain areas, and those are the areas where it will be really bad. As you can see here, we have more points close to each other, and therefore it is smoother. So you need a resample. The resample node, just drop a resample node. The resample node is it's going to, every frame, in this case because we are in a solver, is going to resample your curve, and it is going to make more points. As you can see, it's keeping points at the same distance, but in order to make to keep points at the same distance, it has to add points where they lack, when the points are not. So this is going to create a smooth result, and we will be talking about the resample node of course in other videos, but for the moment just enjoy what you've made and enjoy your curl noise visualization. and see you in the next tutorial.